Hey there guys, happy Thursday. I have one last problem for us to complete in this chapter. And then once we're done, we can move on to some new stuff. Here's what we're dealing with. We're going to load an artillery shell into this cannon and fire it, which will cause the shell to move along this parabolic trajectory that you see on the screen. However, we are only interested in the highest part of the shell's path, because at that point the shell is going to explode into two fragments, like this. Notice that one piece flew backwards to where the artillery was launched from, and the other went off screen completely, some further displacement in the x direction. There's two things that we have to do here. The first is to figure out where the smaller fragment lands relative to the cannon. The second is to calculate the energy released by the explosion of the shell. Before we start, let's figure out the individual masses of the fragments of the shell. The problem description told us that one piece is 3 times larger than the other, and the mass of the shell before the explosion was 12 kilograms. Thus, these two fragments, which I'm calling A and B, their masses need to add up to that amount. So let's take the expression for the mass of the larger chunk, A, from the top equation, and plug it into the second equation on a new line at the bottom. This allows us to add similar terms on the left, resulting in 4 times the mass of B being equal to the total mass of the shell. And if we divide both sides by 4, we find that the masses of our fragments are 3 kilograms for B and 9 kilograms for A. Another thing that's needed is the horizontal velocity of the shell right before it exploded. If we don't know what that is, then we can't apply the conservation of momentum, and that's not good. So let's calculate that next. We'll use this kinematic equation, and let's call the velocity at the highest point in the shell's trajectory v top. Since we're working in the x direction, we can actually simplify this equation by eliminating the acceleration term, because there's only acceleration in the y direction due to gravity. If we plug in the initial velocity of the shell and the angle that it was fired at, v top is about 86 meters per second. And now we can apply the conservation of momentum. Before the explosion occurs, the only horizontal momentum is due to the shell. And then after the explosion, we will have the negative momentum of the larger piece, A, moving to the left, and the positive momentum of the smaller piece, B, moving to the right. Notice that we have V top here attached to the mass of A on the right-hand side. You might be wondering, how are we supposed to know that V top goes there? Well, keep this in mind. We're told that fragment A returns to the exact location that it started from when the cannon was launched. And if that's the case, then it must have the exact same velocity as the shell did before it blew up, but in the opposite direction. So that is the reasoning behind why we have this V top here. And also, it's negative, so that it moves in the left direction. Let's actually take that term and move it over to the other side. We need the velocity of B, so let's divide both sides by B's mass, and also factor out V top from the numerator. Once we plug in our numbers and put everything into a calculator, you should find that the velocity of B comes out to 602 meters per second. We can now figure out the displacement of B, but there's a problem. We don't know how far the shell traveled before exploding. That distance has to be included in our answer when we state where the smaller piece landed. So let's get that out of the way. Now, we could use the projectile motion range equation to get the shell's distance, and that's exactly what we're going to do, but we're skipping steps if we just pluck the equation from the sky and don't show where it came from. We need to justify the use of that expression. So let's start with this kinematic equation here. It's a good spot to begin, but we have no idea how much time it takes for this shell to travel that range. So we're going to need another equation to make progress. There's only one other projectile motion expression that contains the variables that we know about, which are velocities, as well as time. And it's this one. But we need to make an alteration to it. If you recall, back in the Newton's Laws chapter, we encountered this kind of a situation a couple times, where we would work in one direction, like X, we would figure some stuff out, but then we would get stuck, and we would have to flip to the other direction, like Y, to move forward. It's the same scenario here. Instead of applying this second equation in the X direction, we're going to use it in the Y direction instead, which means the velocities will have the sine of theta attached to them, and the acceleration will be minus g. There's a very important thing to remember in this kind of a situation that I'd like to remind us of. Whenever you have a projectile that ends at the same height that it was launched from, the initial and the final velocities in the y direction have the same magnitude. So this means that under these conditions, the final y velocity, which is v final sine theta, found here on the left, that can be rewritten as v initial sine theta, but negative. The goal here is to solve for the time. So let's move the positive term on the right-hand side over to the left, and then divide both sides by minus g. We have negative 2 of the same term in the numerator, and we can also divide out the negative sign upstairs and downstairs. And this is the expression for t, or time, whatever you want to call it, that we're going to plug into that range equation that we started with earlier. And here's what it looks like when we do that. We have two factors of v initial being multiplied together, one here and one here. So we'll end up with v initial squared. And I'm going to group 2 times the cosine of theta times the sine of theta together in the parentheses here. The reason we want to group those is because this trig expression can be simplified to something a bit more compact. Here's another reminder. There's a trig identity that says 2 times the cosine of theta times the sine of theta is equivalent to the sine of 2 times theta. Let's make that replacement in our numerator. And now we finally arrive at a projectile motion equation that might look familiar. This is how that range equation comes about. There's nothing left to simplify, so let's plug in the values of what we know. Using 4 digits and ignoring small fractions of distance, you should get approximately 2,100 157 meters. There's a problem with this result, though. Can you see why? The shell didn't go the full displacement before exploding. It only reached half this x distance. So this means we want to divide r by 2, which will give us 1,079 meters. So this is the first part of fragment B's displacement. For the secondary displacement, we can use another simple relation between distance, velocity, and time. Let's divide both sides by velocity. We don't directly know the time it takes for both fragments to hit the ground, but we were told that they hit the ground at the same time. So this means the ratio of distance to velocity for A and B are equal to each other, and we can set that up like this. Let's use this expression and multiply both sides by the velocity of B to get the distance of B after the explosion happens. Plug in the numbers and stick it into a calculator, and you should get exactly 7,553 meters. So finally, we can compute the total displacement of B and state where it lands relative to the cannon by adding these two x distances together. Thus, the final answer to the first task of this problem is 8,631 meters. Next up is the explosion energy. If we take the total kinetic energy of the fragments and subtract the kinetic energy of the shell right before it explodes, we'll get the energy released by the explosion itself. All we have to do here is just plug in the values that we've obtained from before. Super easy. To make the expression slightly smaller on the screen, I'm going to factor out 1/2 from each term on the left. And now, let's plug in some numbers. Answering to 3 significant figures, we're going to match the answer found in the book for this problem of approximately 5.33 times 10 to the 5 joules. And now we are done. The momentum chapter is over, and we're ready to move on to the next one, which involves the rotation of rigid objects. I'd like to take a moment to thank you all for your time, your patience, and your engagement as we've worked through this material. I really do appreciate it. But for now, that's all I have to share. Take care, everybody.